Okay, so AC circuits, right?
Polarization.
Oh yeah, polarization. Yes. Yeah, polarization is relatively straightforward. Okay. So, so this is polarization. Okay. So this is the idea of vector, pretty much vectors. Remember that intensity of light, intensity has to do with energy density, energy per unit volume, if you want. That's proportional to, right? That's proportional to, it's actually half of, right? Electric field square, right? So it's electric field dotted with electric field. Great. And the electric field is a vector. But in some plane, like if the electric field is in a plane, the property of a vector is that if you were to project it in a particular direction, right? So let's say this is X component, correct? If you project this in a direction, let's say this is theta, electric field dotted with X hat is equal to the magnitude of the electric field, which I write without a vector, times cosine theta, correct? That's a simple idea of a vector. Right? Its component it picks up that angle. So now what we want to do is, let us say there is a beam. So I think I can use this straight line idea. So this is a optical axis. Right? And let us say there is a beam. Let me try to draw using straight lines. Right, that's your beam. So this is just a line that is coming through. And let me actually draw two more lines. So it's like a window, right? Oops. Pretty much like a window. And let me have an electric field that is on this plane. So that's an electric field. That's E. Let it make an angle theta with respect to the x-axis. So let's say this is the y-axis, and that's your x-axis, and this is your z-axis. Right? That should be clear. And that's a vector. The electric field, whenever we think of light, light is basically oscillations of electric field. So the electric field is keeping on oscillating and it is keeping on moving forward. Now let's think of a material, like pretty much a material that has a property that it can pick a component. So this is what is called a polarizer. So this is a polarizer now. A polarizer has this feature. Again, I'll make this like a window. That's your window. So this is a polarizer, and what is its property? So this is polarizer. Along x hat. Okay. So that means to say that it will pick only this component. So it will stop the component that is vertical. So I'm going to break this vector into two. So it had two components, the y component and the x component. The x component is allowed and the y component is not allowed. So a polarizer allows x component stops the y component. It doesn't have to be always along the x direction. In whatever direction the polarizer works, correct? That's the idea. So what is the electric field now? So electric field prime here that's passing out, that's equal to E. So it's in the x direction first of all. It's in the x direction. Hat direction times the original E dotted with x hat, which is E cosine theta.
Sir, what is E dash?
E prime is the new vector. So this is the new vector here, right? So after it passes through the polarizer, that's the electric field. Does that help?
Yes, sir.
The new vector is only having an x component. And the question is, what is that electric field? Is that clear? Did I answer your question?
Yes, sir.
Okay, good. So that's equal to x hat times E cosine theta. Okay, that's your new electric field. Intensity, remember, so original intensity. So original, let me write it in black. So original intensity, let's call it I naught, is equal to, or let's say proportional to, half E square, right? Final intensity of light is I naught prime, which is proportional to half E prime, correct? E prime square. But E prime is E cosine theta, so you square that out, so that's equal to half E square times cosine square theta. So what we have learned is that I naught prime is equal to I naught times cosine square theta. Question?
You're saying sine and writing cos?
Did I write sine? Did I say sine? Oh, sorry.
You said cosine.
Oh, I said cosine. Yeah, cosine theta. Okay. Yeah, maybe cos. Yeah. So yeah, that can lead to confusion. But yeah, cos theta in full form is called cosine theta, right? Yeah. So cos theta. Got it. Okay. Yeah, I'm not used to saying cos. Yeah, so I say cosine usually. Yeah. That's actually a good point. When I teach, probably half of the students might be getting confused. No one says anything. Yeah, thanks. Okay, so overall the idea is, notice what is happening. The electric field, since light is built out of electric field and it's a vector. When it passes through a material, a polarizer, that polarizer has the ability to take a component of the electric field. That's the simple idea. It does not allow Y component. It allows only the X component. Okay, so that's the idea of a polarizer. But overall what is happening is the intensity. What we measure is intensity. We don't usually measure the electric field directly. What we see at least is the intensity. So intensity is square of the electric field. So that is giving a cosine square theta that shows up. So if your polarizer was 90 degree with respect to, so let's ask the question, as an example, let's say, right? Like if theta is equal to 0, I naught prime is equal to, like cosine of 0 is 1, so is equal to the original intensity itself. So you don't see any difference, right? Yes. But if theta was equal to pi by 2, then the intensity that you see is dependent on cos of pi by 2, and that's 0. Right? So it is possible to, so maybe you have seen these materials, maybe in a lab in your school, or sometimes even some of the sunglasses that you see, they have this property that if you were to look at something and you rotate the glass, then the intensity reduces significantly. And if it is a proper polarizer, it will actually become dark. You won't be able to see through anything if you turn it around. Is that clear what I'm saying? Like, is the explanation clear? Of course, you can put something in between. Theta is equal to pi by 4. Right? So I0 prime is equal to I0 times cosine of pi by 4. And how much is cosine of pi by 4? So that's cosine of pi by 4 is 1 over root 2. Correct? Yeah, so square will be 1 by 2. Good. So it is so I naught over 2. Right? So if you rotate it by 90 degrees, you get 0, but somewhere in between, exactly halfway between them, you get a exactly reduced by half. One can always ask what happens if you go beyond. You can see that theta is equal to pi acts like theta is equal to 0. Right? So it is insensitive to, it is a squared quantity, so it is insensitive to changing the direction. Right? That's equal to I naught. Okay. And often what in how problems are created out of this is that you will make a chain out of this. Like the first intensity comes out as I square over 2. Again, you put a polarizer in front of it. And you run it through that. And again, it will decrease by a factor of half or whatever is the angle. And that's the way you will construct a problem based on that. Usually the problems made are relatively easy on this. Okay, does that help? Okay. Okay, so at this point, I think it is good to jump to AC circuits, I think, because I think there's a good stuff to cover there. And with a reasonable understanding of that, we should be able to.
Polarization law is there in this? Brewster's law. Brewster's law.
Oh yeah, what is that? Brewster's? Yeah, what was the question? Yeah, what is Brewster's law, right? Yes. Yeah, again, that's just a. Oh, I can explain this nicely actually. Yeah, let's see. Yeah. So that's not related to okay, yeah, it is related to polarization in a sense. Yeah. Cover again?
No, we are talking about it.
Okay. So let's talk about reflection now. Okay. or refraction. So this is what is called Brewster's angle, right? And Brewster's angle is named after this guy Brewster himself. I think, yeah, I don't know. It's not recent. I think it is long before. I think during optics, it must be late 1700s and all that. Okay. So either way, so let's see. So what we want to investigate is you have a material. So that's an interface, let's say. Yep. On one side of the material is refractive index N1. Oh, so you use mu, right? So,
No, it's okay, sir.
okay. So
We
this
use
is.
both the letters.
So you use both N1 and mu1. Okay. So I can use mu since I changed it anyway. Yeah. So this is mu1, and let us say mu2 on the other side. Okay. And let's, just for making it concrete, let us say that mu2 is greater than mu1. So example is, this is glass, and that's air. Okay. And we want to ask the question, a ray of light comes, how much goes into the light and how much goes out, or just refraction, simple refraction, but a little more in detail. Okay, so let's think of a ray of light, and let's say it is coming this way. So that's a ray of light. So that's a ray of light. And we are interested in the electric field. Okay, so let me try to draw this. So that's maybe straight line. So that's electric field associated. So electric field is always perpendicular to the direction in which the ray is traveling. So this red vector represents the electric field E. In fact, it represents the electric field in the first medium. Okay. Now, usually we think of reflection and refraction as Snell's law, right? N1 sine theta 1 is equal to N2 sine theta 2. But that's a very simple version. You want to think about it in terms of vectors now. So let me write that Snell's law. Snell's law is N1 sine theta 1 is equal to N2 sine theta 2, right? And where is sine theta 1 here? So let's, that's your theta 1. That's theta 1. Okay, that's that angle with that it makes with respect to that. But we want to think in terms of vectors. So what does this Snell's law look like for vectors? What it is doing is that it keeps the, notice this has a vertical component, right? And it has a horizontal component of the vector, correct? This is called a perpendicular mode. So these are the two polarizations of the wave, if you want. When a light comes in, these two vectors are called the polarization modes. So this is called the perpendicular mode. And this is called the parallel mode. In literature, these modes are termed differently. Sometimes they're called the transverse electric and transverse magnetic. Sometimes they're called the P mode and the S mode. Either way, it doesn't matter. No one will ask you what mode it is. What you have to understand is that there are two modes. And these two modes behave differently during reflection and or refraction here. So how do they behave? So that's what our interest interest is in. So we are talking about Snell's law. So the first result is that the perpendicular mode remains the same. Perpendicular mode remains same. So the component that is along the plate remains the same during refraction. And the second is the parallel mode. Parallel mode satisfies the parallel mode satisfies something like Snell's law. So you have N1 times E parallel, right? E parallel square, let's say, is equal in the first. So this is comma. So this means parallel. Let me. How can I write this? So let me write this as E1 X. Okay, so this is means parallel mode. So the X component of this squared times N1 is equal to N2 times the same component squared. What we need to know is that since they are the same at the interface, if N2 increases, that means electric field has to decrease. Right? These two are the same. If N2 is greater than N1, then E2x is less than E1x. Clear? Okay. So what is happening is, so after it reaches the interface, this decreases. This remains the same. So this blue lines represent the vectors after going through the medium. The perpendicular mode remains the same. Parallel mode decreases. Right? It has been shortened a little. That means to say that the vector will change now. The vector is no more as long as it was. Instead, it is here like this. That's your new vector. So that's E2. Is that clear what happened?
Yes.
The X component has decreased, so the vector has changed. Once that vector is changed, now we can draw its new perpendicular line. Notice the way in which it is moving is perpendicular to the electric field. So the electric field perpendicular to that is this. Right? That's your vector. That's your ray, if you want. Right? So that's your ray. And this is angle theta 2. Agreed? Okay. So these two modes decide what refraction is. Okay. Now, interesting part is the Brewster's angle. So the idea is in statement, two modes behave differently. The two polarization modes behave differently during refraction. Okay. And Brewster's angle is one mode can go to zero. Only one of the modes, not both, okay, can go to zero after refraction. can, right? It is not always. If the angle is correct, this one of the mode alone can go to 0. And when that happens, that is called Brewster's angle. So when it happens, when it goes to 0, it is called the Brewster's angle. Okay. So theta 1, so the condition is that theta 1, when it is equal to theta b, right, that is the Brewster's angle, at that point, the condition that is at theta 1 is equal to theta b, such that tangent theta b is exactly equal to n1 over n2. Right? If this condition is satisfied, there is no refraction at this angle. There is no refraction of one of the modes. It is reflection and refraction actually. Okay. So that's okay. Okay. But one more condition you should remember is that at theta 1 equal to theta b, the incident angle plus the refracted angle, theta 1 plus theta 2, is exactly equal to 90 degrees or pi by 2. This cannot be shown immediately from here, but you have to accept it as a statement. The derivation of this takes a lot of work, so we cannot go through that here. So this is a law, you can say. So that's why it's called a law, right? But this can be derived from more modern equations. Right? So these two are Brewster's law. Right? I haven't derived this for you, but I have explained that there are two modes, they reflect differently, but one of the mode can go to 0 at a very special situation, and that is the Brewster angle. Okay. It's more, and this is as an application. How does your sunglasses work? Sunglasses work exactly like this. You have a material which is having polarizations, which actually filter this one of the modes. So if both modes are coming, that is intensity is very high, but your sunglasses is able to filter one of these modes in the sense that it can cancel away this. So get rid of one of the reflections and you have less intensity, and that is how your sunglasses work. A very simple way of sunglasses. Okay. Of course, color is another way of using a sunglass, but these are polar. You might have seen it as a polarization mode sunglasses. Have you heard about this?
Yes.
Sunglasses having polarizations, sensitive materials?
Yes? UV polarization.
Yes. Yes, UV polarizer, exactly. That's what it's called. Yeah, that's correct. Good. Okay, so that's the idea behind it. Again, as far as problems goes, I think the only thing you need to know is the tangent of Brewster's angle is n1 over n2. It's more of a knowledge-based thing. You cannot derive it based on whatever you have learned at this level. You need more information for that.
We don't have the derivation of it, sir.
You don't have this relation?
No, we don't have the derivation for Brewster's angle. We just have that relation. Tan theta is equal to n1 by n2.
Exactly, yeah. That's because it is a long derivation. It requires what is called the Green's functions. You have to derive the reflection coefficient. But it can be done. I mean, somewhere 1 year, 2 years down the line when you're doing engineering or some other, if you take more physics, then it is possible to derive it. It's a textbook material. Okay. Okay, so shall we proceed to another topic, or is there a question you have on this? Any comments?
We'll proceed, sir.
You can proceed, okay. Did Radha sir wanted to do anything with the recording?
He's not here.
He's not around, so let's proceed, okay? Okay.
What do you want? Sir, recording with the stop on one.
Sir, stop recording. 1 second.
AC current put on.
So now we're going to start a new topic, yeah. Sit down, it's easier.
Yes. Yeah, one, three. Let the man open. I'm going to problem speaker
Okay. Well, the path difference is. So you guys have this problem with you? It's K units.
We are not there, only one had a problem.
Oh.
Hey, it's good.
It's lambda over 3, I think. Yeah, lambda over 3. Right. Okay. So we had earlier said yesterday that in double slit, the condition for interference is given by d sine theta is equal to what was it, n lambda, correct?
Yes.
For maxima, and it is n plus half lambda for minimum. That's one way of writing it. But this condition actually comes from an interference term. So this is a result I gave. Usually what happens is that you have one wave. So let's say amplitude A total is equal to A1 plus A2. Right? These are the amplitudes of two waves that is coming in. And the interference of this is given by the formula A1 square plus A2 square. Let's think of this as vectors. So it is plus 2 times A1 A2 times there is a cosine of the path difference. So this is thought of as path difference. And A1 and A2 should be interpreted as amplitude. And the path difference, delta phi, is pretty much d sine theta itself, but you interpret it in the following way. It is 2 pi, or let's say, 2 pi times d sine theta over lambda, like the ratio that you have if you were to divide that by lambda, and that's equal to 2 pi times n. This is for maximum, and if you have 2 pi times n plus half, you have minimum. So it is the same idea, but we are writing it in terms of angles. Instead of writing in terms of distances, we are writing in terms of angles. So d sine theta, just divide out by lambda. And that's understood as the path difference. Now, in this way of writing, there is a nice interpretation. This is intensity of light. That's equal to the intensity of the first beam, first wave, plus the intensity of the second wave, plus 2 times the intensity of the square root of the first times second, times cosine of delta phi, whatever the angle is for that particular case. Okay. Now, what they have told us is that if the path difference is lambda, that means the path difference is n equal to 1. So cosine of 2 pi is, so for n equal to 1, so given lambda leads to k, right? That means for n equal to 1, which means that cosine of 2 pi, so that means delta phi is equal to 1, is just 2 pi. So the intensity is equal to I1 and I2 are the same, so same wave is coming through. So that's 2 times I, so it is 4 times. So this is I plus 2 times I times cosine of 2 pi. Cosine of 2 pi, cosine of 0 is 1. So that's equal to 4 times I. Let's call it I naught, right? So I1 or I naught, let's say. So 4 times I naught. And that's given to be K. And now we are asking, what happens if lambda is lambda over 3? So what happens if if lambda was equal to 3? So lambda over 3 implies that that's n over 3. So you can say that's 1 over 3. So delta phi is equal to 2 pi over 3. And our intensity is equal to I naught plus 2 times I naught times cosine of 2 pi over 3. Cosine of 2 pi over 3 is cosine of 120, right? Cosine of 120 is how much? So it's minus of cosine. So that will be 2 times I naught times 1 plus cosine 120. One plus cosine 120 is, I guess, help. So it's 1 minus cosine 30, I guess. And cosine 30 is sine 60, so that's root 3 over 2. So 2 I naught times 1 minus root 3 over 2. Right. But we know 4 I naught is k, so that's equal to k over 2. Times 1 minus root 3 over 2. So the idea here is that I think which I didn't convey last time is that intensity is related to these conditions through this path difference. So there is the idea of path difference, and which indeed is related to intensity via the amplitude. So interference works with amplitude and the path difference, and the condition for maxima minima is given in terms of cosine of an angle going to 1 or 0. Like remember, cosine of 0 is 1, cosine of pi is minus 1, and cosine of pi by 2 is 0. So that's your maxima minima condition. So this is a way of translating your maxima minima conditions into an angular region. So it's more conceptual, but yeah, so it was a good question. Yeah. Did this help?
Yes, sir.
I mean, later, I think other problems are better to work on. This is more conceptual. I had to go through the procedure, I think.
I think this is from NCRT book, Rajesh.
Huh?
NCRT book, backside.
This one. Oh, okay, okay. So what does that mean? They are usually harder, easier, or?
It's in a portion, sir.
Oh, it's in your syllabus. Okay, 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 okay. So that means I should have passed on. I should have taught that in the beginning itself. Yeah. I mean, usually how you work out is that you begin from here and then reach that condition, and that condition is what is used in the problem. But then when you teach at this as a problem level, so you only teach the conditions. But this is how you begin, by saying that, oh, there is a amplitude, there is a phase for each wave, and the phase difference is defined as the path difference, and that is how it leads to that. It's more conceptual, yeah, but good point, yeah. Very good question, yeah. Helps?
Yes.
Hopefully, yeah. So, Radha, you want to check your video at this point, or should I keep proceeding?
I think we checked. Perfect.